Yes, it's Uncle Jegz, and this is the second video of the Corona lockdown lessons. I'll be looking at equations and calculations today. This is mainly gonna concern reacting masses calculations. Not gonna lie, bare students flop this section. But hopefully after this video you'll be laughing when you see these questions. First, you know what to do. Have a go at these retrieval questions, pause the video, attempt, and then play when you're ready, okay? The first question is 6.02 times 10 to the 23. Then silicon dioxide is a giant covalent structure. Then for the last question, as you go down group 1 elements, the reactivity increases because the outer electron is further away from the nucleus, which means it's easier to lose. And as you can see from our success criteria, this part of chemistry is not found in the foundation paper, so therefore foundation students, you can skip this one, yeah? Now before we get into the meat and potatoes of this lesson, let me just make sure you have the particulars necessary for entry to this class. Calculate the number of moles in 45 grams of H2O. If you are completely baffled by that, make sure you check out how to calculate moles in this card over here. The rest of you, if you're cool with this, pause, attempt, and then play. Okay then. Moles is equals to mass over molar mass, so that is 45 grams over 18, which is the molar mass of our water. That gives us 2.5 moles. So let's pattern this first row in one go. You've probably heard about the conservation of mass and energy. This just means that energy or mass cannot be created or destroyed. It can only be transformed from one state, one form to another, alright? Let's look at this hypothetical reaction. A and B react together to produce C. Your arrow points away from your reactants and points towards your product. According to the law of conservation of mass, the mass of our reactants is equal to the mass of our product. Let's look at this reaction. Does it obey the law of conservation of mass? Well, we can find this out just by counting the number of atoms we have of each element on both sides. Start by writing out the equation. Then draw a line down from where your arrow is. Next thing, write out the elements you have on both sides. The elements on the left hand side should be the same as the one on your right hand side. Make sure that each element is on the same line on the left and right hand side. That just makes it easier. Next, you tally how much of each element you have. For the left hand side, we have hydrogen with a small 2 on the right hand side. This subscript 2 tells us that we have 2 hydrogen atoms within that one molecule. So that looks like this. 2 hydrogen atoms bonded together. You should then be able to clock that means that the oxygen is the same. We have a subscript 2 on the right hand side. The right hand side is H subscript 2 and O with no subscript on the right hand side of it. When an element has no subscript on the right of it, that just means that there's one of it, okay? And since we have a subscript 2 on the right hand side of the hydrogen, this formula tells us that for one molecule of water we have 2 hydrogen atoms and 1 oxygen atom. You should have clocked that we don't have the same number of atoms on the left hand side as we have on the right hand side. The hydrogens balance out, but the oxygens don't. This is the whole purpose of balancing equations, to make sure that we have the same number of atoms on the left and right hand side of our equation. So balancing equations is just a way to make sure you're not breaking the law of conservation of mass. Alright, cool. Let's see how we actually balance this equation then. The golden rule of balancing equations is that it's only the big numbers in front that are allowed to change, okay? You can only add or change the big numbers at the front. Do not touch the small subscript. Changing the small numbers changes the whole molecule, which then changes its structure. We saw that water is H2O and it looked like this. Adding another oxygen makes it hydrogen peroxide, which looks slightly different. And you're looking at these two substances and you think, oh, that's not too bad. Just look at these two reactions. When we add blood to water, it doesn't really do anything. But when we add blood to hydrogen peroxide, you see that thing there. So yeah, you don't change the small numbers because you change the molecules, which has the potential to change the chemical properties and everything else. So we start by tallying the atoms that we have on both sides. I need to balance the oxygen, and we only add or change the big numbers. I need 2 oxygens on the right hand side. We do this by multiplication. It's not addition, okay? When you're adding these big numbers, you're multiplying. That means that I'm not adding 1, but I'm multiplying by 2. Now we need to reflect this change in our equation and then in our tally so we can keep track of our atoms. So 2 moles of water means that we have 2 times 1 oxygen, which gives us 2 oxygens. Our oxygen is now balanced. But look, now we have 2 moles of water, which has also changed the number of hydrogens on the right hand side as well. So now we have 2 times 2 hydrogens, which gives us 4 hydrogen atoms on this side. Now we have to go back to the other side because our hydrogen isn't balanced. So you've guessed it, we need to multiply the left hand side by 2. So we add 2 to the front, we multiply by 2, 2 times 2 hydrogen gives us 4. Our equation is completed. Now have a go at this example. It's exactly the same steps as before. You do that line in the middle, you tally your elements on both sides, and you keep multiplying by the big number in front until both sides have the balanced equation. Pause, attempt, and then play. We have 2 hydrogens and 2 chlorines on the left hand side, but we only have 1 of each on the right hand side. Without changing the subscript, we need to multiply the right hand side by 2. So we add a big 2 in front of the right hand side. Now the equation is balanced. Now try this one. This one's slightly gonna be longer, but just firm it. When you get these combustion reactions, this is the order that you should balance. First balance the carbon, then balance the hydrogen, and then balance the oxygen. On the left we have 3 carbons, 8 hydrogens, and 2 oxygens. On the right hand side we have 1 carbon, 2 hydrogens, but 3 oxygens. 2 on our carbon dioxide, and 1 on our water. To balance the carbon, we need to make sure we have more carbon dioxides on the right hand side, so 3 moles. 3 times 1 carbon gives us 3. But now we have 3 times 2 oxygens here, which gives us 6 oxygens on here, and plus that extra oxygen on the water over here. Now we go on to balance the hydrogen. We have 8 hydrogens on the left hand side, but only 2 on the right hand side. To balance this, we need to multiply the right hand side by 4. 4 times 2 gives us 8 hydrogens on the right hand side. Now our oxygen has changed once again. This is one of the reasons why I recommend saving the oxygen to last, because it keeps changing. 4 times 1 oxygen gives us 4 oxygen atoms over here. Plus the 6 that we already had over here gives us 10 oxygens on the right hand side. Now to get 10 oxygens on the left hand side, we need to multiply by 5. So 5 times 2 oxygen gives us 10 oxygens. Boom. We can chop the last 2 success criteria in one go as well. This next section is called reacting masses. Reacting masses is just a natural evolution of the conservation of mass. Let's look at this reaction. This equation tells us that 2 moles of hydrogen and 1 mole of oxygen produces 2 moles of water. Remember from the last video that moles equals your RAM, or relative atomic mass, or your relative formula mass, RFM, in grams. Each hydrogen atom has a RAM of 1, meaning that 1 molecule of hydrogen has a relative formula mass of 2. But since we have 2 moles, we have 4 atoms of hydrogen. So 4 times 1 gives us 4 grams of hydrogen here. 2 lots of oxygens means that we've got 2 times 16 oxygen, which gives us 32 grams. We have 2 moles of water, which means that we've got 4 times 1 hydrogen and 2 times 16 oxygen, which gives us 36 grams of water. This means that if we react 4 grams of hydrogen with 32 grams of oxygen, we should produce 36 grams of water. A typical question for reacting masses will look something like this. Calculate the mass of oxygen that must react with hydrogen to make 45 grams of water. We simply need this equation. Moles equals mass over molar mass. Let's first identify what we want to work out. That's the mass of oxygen. What mass have we been given in the question? We've been given 45 grams of water that's been produced. Make sure you follow this pattern of steps here, and I've also color coordinated it. I've given it some drip to help you follow where these numbers are coming from. Step 1. Write out the molar masses of each of your substance just below the formula in the equation. Number 2. Write the mass of your substance from your question above that substance in the equation. As you can see, mass over molar mass gives us our moles. So 45 grams over 36 grams gives us 1.25 moles. But the question's asking us to work out the mass of oxygen. Look at our equation again. Mass equals moles times molar mass. So the mass of our oxygen is that moles that we just worked out, 1.25 moles times the molar mass, which is 32. This gives us 40 grams of oxygen. So now have a go at this example. Pause, attempt, play. Just follow the same steps I gave you, right? We want to know the mass of carbon dioxide produced when 24 grams of carbon reacts completely with oxygen. First, we write the molar masses of each underneath. 12 for carbon, 44 for carbon dioxide. Let's not worry about the oxygen. That can move. Then the mass in the question, which is the 24 grams of carbon, we'll put that above the carbon. Moles is mass over MR, our molar mass. So that's 24 grams over 12, which gives us 2 moles. Mass equals moles times MR, our molar mass. So 2 moles times the 44, which is our molar mass, gives us 88 grams of carbon dioxide produced. Light work. Lesson done. If you didn't get any of that, check below for the timestamps, yeah, to skip to the section you need to work on. Alright, I'll catch you guys next week in a bit.